All right, let's look into the future. 2 days from now, you'll have homework 13 due. That's noise pollution. We've already taken some of the concepts that's on that assignment. Today we're going to do the other two components of the assignment as examples. Also as a reminder, Sunday is the last day to go and do your Writing Center appointment. I've got a handful of emails from the Writing Center indicating that you've been over there and done the appointment, but not many. So if they run out of appointments before the deadline and you can't do it, then it's just too bad. You don't get the points. 5 o'clock, yeah. Or if they're open till midnight, if you can convince someone in the Writing Center to meet you at 11 p.m., yeah. End of the day is when you need to conclude that assignment, the meeting. Any questions related to the announcements? All right, today we're continuing to talk about noise. And what is noise? Our quiz was a good example of the definition of noise because there was plenty of it out in the lobby. What's the definition of noise? It's any unwanted noise, any unwanted sound. And so the difference between music and noise is whether or not you want it, I suppose. It's irrespective of the volume. It's just whether it causes a physiological or a psychological disturbance. So how much noise is too much? There's a lot of really great information in the book. Different ways and different studies that have been done on how much noise disturbs people. One way to look at it is how far away you are from the person who's speaking to you. And this is a real problem I have with my kids because they'll be upstairs in their bedroom and I may be in the kitchen washing dishes, and so it's a noisy environment, and they're just talking to me as though I'm standing right next to them. You know, Dad, where's my hat? What? I can tell someone's talking, but I'm so far away from the speaker that the surrounding noises sort of make it difficult to communicate. And so this figure is showing how far away you have to be from someone and how noisy the background environment is and whether or not it's possible to speak. And so if you're in an area where it's 100 decibels, maybe a noisy club, you have to shout directly into someone's ear. You have to be very, very close for there to be just difficult communication. However, if you're in a very quiet environment, like if you've ever been into the main building, maybe after 5 p.m., when everyone's gone home, you could speak in a normal voice and 9 meters, maybe even 20 meters away, it'd be very easy to hear someone. So I thought this figure is interesting because on the vertical axis, it's talking about the environment that you're in, how noisy it is. Horizontal axis is the distance away from the person speaking. And then you can see, based on how far away and what the noisy environment is, whether or not communication is possible. Another way of looking at it, the FHA in the United States is the Federal Housing Authority. And they're a government body that helps people to buy homes by making loans. And so they set up a lot of rules that are supposed to ensure the quality of housing. Usually it's building codes. But one of the things that they look at is how noisy it can be in the environment where a house is built and still qualify for these federally subsidized loans. And so they classify different categories. For example, when there's supposed to be an area that should be very, very quiet, like a cemetery or a park, they're saying that there's a category A. And then they say, in terms of decibels, what the maximum limit of the noise should be. And we're going to talk about both of these concepts today, the LEQ and the L10, but they're just sort of like statistical measures of how often a certain noise threshold is violated. So for example, if it should be very quiet, a very, maybe a neighborhood area, they're saying that 57 decibels would be a limit. However, if it is an area that is maybe just commercial activity, like factories or shopping, the noise limit could be 72, and they're saying inside of a building like a hospital or a school, the noise level shouldn't exceed 52 decibels. And so there's a variety of international standards that classify the relationship between how noisy an environment should be and how the space is being used. And so this is kind of analogous to how we talked about water quality. How clean the water has to be depends on how it's going to be used. In the same way, how serene and quiet an environment should be depends on its use. And so you don't necessarily need to preserve the perfect quiet if there's undeveloped land. And so in undeveloped land, they're saying that there's an unlimited amount of noise. If no one's using it, you might as well, I don't know, do whatever the noisiest activity is that's needed. Here's another table that's in the text. It's from the FAA, which is the Federal Aviation Administration. And so this table has to do with the effect of air traffic on different types of land uses. And they're saying that a limit on areas that are used for commercial activity would be between 80 to 85 decibels. And here's another type of limit, the LDN. That's talking about a way of calculating the average noise over a day, and you actually weight it so that there's more of a penalty at night. For obvious reasons, we want it to be more quiet at night, and so the nighttime hours, there's an additional penalty for any excess noise during the nighttime hours. And so that's what this LDN is saying. And so a place that is supposed to be for schools, you can see that they would have 65 decibels as the maximum limit for a school area. But places that are for manufacturing and production, it's fine for the noise levels to be above 85 decibels. And so they're hopefully trying to route air traffic over places that don't have schools and people who are living, and route the air traffic over industrial areas instead. Remember that the cause of noise is vibration, where it's the vibration of my vocal cords or the vibration of two objects colliding together that causes a tapping sound. Even a speaker that maybe is installed in your house or in a car that's making sound, you can sometimes look at the cone of the speaker and tell that it's vibrating. And it's the vibrations of the speaker that's causing the noise. This figure is from the text, and it makes an illustration of how you can isolate those vibrations so that unwanted noise doesn't propagate. So for example, if you had a very noisy piece of equipment, and an example of that in civil engineering would be a water pump. Water pumps can be very noisy, and so sometimes when groundwater is being pumped up to the surface, then they'll put the pump head inside of a small shack that's essentially to help keep the noise inside the shack, and it also helps to keep the area secure and safe from corrosion. But by soundproofing the room, that would be putting in acoustic lining that's similar to insulation. It can be made out of fiberglass or it can be made out of plastic foam. It's just something to try and absorb the vibration of the sound. You can see that they're isolating the noise source by putting it onto springs, because those vibrations can even propagate, low frequencies can propagate through the ground, and it wouldn't even need to be through the air that the vibrations can travel. Sometimes the entire ground could be vibrating, and then the sound could be emitted outside of the surrounding structure. Another couple key points about this, what it's showing is that if you could have walls that aren't touching each other, then that's another way to isolate the vibrations, because as soon as you put a beam that's connecting all of these walls, then the vibration travels through the beam, and then it turns this exterior wall into a vibrating source. And so having walls that are sort of independently anchored is a good strategy of isolating the vibration and limiting noise. All right, so here is one of the questions from your homework. It asks you to find the equivalent continuous energy level. It's a way of having a weighted average over time. Sometimes it's going to be noisy, sometimes it's going to be quiet, and what this LEQ calculates is a time-weighted average of the sound. And so here's the formula. You add up all of the decibel readings. L sub I would be the measurement in decibels. And we've done a conversion similar to this before to turn it into like the sound power level. So you're finding the decibel, converting it to the sound power level, and multiplying it by however much time it's that volume. So let's take, for instance, this figure on the lower right. What it's showing is that for 10 minutes, what we have is 90 decibels. And then for 30 minutes after that, the noise level is at 70 decibels. And so it doesn't work if we just do a simple average. A simple average would be 90 plus 70 divided by 2. For obvious reasons, that doesn't work, right? Because for one thing, the 70 decibel time was longer. And it's also not as easy as just saying 90 times 10 plus 70 times 30 divided by 40. That wouldn't work because decibel is a nonlinear scale. And so what this function is doing is it's taking the nonlinearity out of the decibel measurement so that we can weight it, and then it's putting the nonlinearity back in with this log term. So what I'd like you to do is, on the handouts you've got for today's class notes, try and calculate what is the LEQ using this formula for the sound description that we've got here. 10 minutes of 90 and then 30 minutes of 70. Okay, here's the solution to this one. So our first sound is 90 decibels, the second is 70. We know the times. So the way that you use the function is you take 10 to the decibels divided by 10. So that's 10 to the 9th power times 10 minutes. And then 10 to the 7th power times 30 minutes and divide that by 40. Take the log of it, then multiply it by 10. It should be 84.1 decibels in the end. So that's how you do a time-weighted average of sound. Okay? Give you a minute to copy that down, just get the idea. I'm sure that you've noticed that the library has some new sound-absorbing materials in the staircase. Has anybody seen that? It's like hanging pieces of foam. It seems to work really well. I remember I was here when the library first opened, and it was a lot noisier back then than it is nowadays. They've done a lot to sort of keep the environment more quiet in the library. Let's move on. Okay, we're going to go through a procedure to predict highway noise. And it uses something called a nomograph. Does everyone have this strange-looking nomograph? Okay, you're going to use one side today for the in-class exercise, and you can use the other side for the homework. So keep this paper with you. You don't need to turn this in for the in-class exercise. What you will turn in for the in-class exercise is the one that you should write your name at the top. So what I'm going to do is I'm going to step you through the process of predicting how noisy a highway is going to be. So on the table in front of you, you should have your notes so that you can refer to what step we're on as we do certain things. And then you should also have the nomograph. And then when you're finished at the end, you can write the answers on the in-class exercise. So the two things we're going to sort of be switching back and forth between is the instructions, the step-by-step instructions, and the nomograph. All right, so in the in-class exercise that you've got, it describes a situation of, let me zoom in here. All right, it says that we've got a proposed highway that is going to be 110 meters from a sensitive area where we want to preserve the quiet. So it's going to be 110 meters away. So that's a piece of data we're going to need. We're going to calculate something called the L10. And L10 means it's a certain volume level that is exceeded 10% of the time. And so it's kind of like that's not as noisy as it ever gets, but it's only exceeded 10% of the time. It's sort of the threshold above which 10% of the time is noisier and 90% of the time is quieter than whatever this amount is. What we know about the road that's going in is that the automobiles and medium trucks are moving at 110 kilometers per hour. The faster they're moving, the more noisy it's going to be, for obvious reasons. The traffic volume is there's 400 cars per hour, 50 medium trucks per hour. Something you should know is that for noise studies, medium trucks count as 10 times as noisy as a car. So we're going to add together the total volume of traffic, and it's going to be 400 plus 500. And so the 500 comes from 50 times 10, because a medium truck is the equivalent of 10 cars in terms of noise. That's just how it's handled. This is an empirical method that is very roundabout in ultimately obtaining the volume. We're assuming there's no heavy trucks, and let's first do this problem by saying that there's no shielding going on. We just want to know what's the noise level before we try and put up maybe a wall to keep the noise levels down. All right, does everyone understand the situation so far? Okay, so take the nomograph. We're going to work with the top one to begin with. And let me show you what the process is. If you have a pencil and a straight edge, that's best. If not, try and draw a line as straight as you can. But we're going to first do step one, which is draw a line from the pivot point through the speed and into line 1. So what I mean by that, pivot point, here's our pivot point, through the speed of the cars. So our cars are moving 110, and then stop it at line A. So there's 2 points. Pivot point, speed of 110, draw a line through them, and then stop the line at A. All right, I'll give you a moment to do that, and then I'll bring up what it should look like. We have no heavy trucks. So far we're just doing the speed, which is 110 of the medium trucks and the vehicles. So we're going pivot point to line A. All right, so that's probably enough time for you to draw a line. All right. Let me give you just one more minute so you can do it. It's going to get a lot more complicated, so we got to keep moving. All right. So here's what it should look like from the pivot point through 110 and stopping at line A. Label that A1. Okay? If you fall behind, I'm recording this, all right? So you can come back to the recording and review the process from beginning to end if you do get left behind. Okay, so the next step is we want to find our volume, and so 900 vehicles per hour is because there was 400 cars, 50 trucks, and the 50 trucks count as 500 because it's a 10-to-1 ratio. So find 900 vehicles per hour, and this is a logarithmic scale, so it shouldn't throw us off that the lines are sort of getting closer together as we go up. So here's 900, and go from point A1 over to 900. Those are the two locations that form this next line. The two locations being 900 on the V axis and A1. And then label the point that it crosses line B, label that as B1. It's written in the text. Yeah, it's just a standard assumption that the medium trucks count as 10 cars. If we have heavy trucks, then we use this upper axis, but in your homework problem, there are no heavy trucks as well. All right, so does everyone have B1 indicated here on the B axis? Okay. Obviously, if you are a little bit sloppy in where you put the lines, then your answer is going to be off in the end. Even if you do it perfectly, it's really only accurate to maybe 1 or 2 decibels. But the more imprecision you introduce along the way, the worse your results will be in the end. All right, so that's step 2. Here's step 3. Go from point B1 to the line of sight distance, also in our case, we're calling that the distance to observer, the distance from where we're interested to the road. And so in the problem statement, it says that this, the road is going to be built 110 meters away. So logarithmic scale, here we have 70, 80, 90, 100, 110 is the next line. So from B1 to 110. And then once you've drawn that line between the 2 points of whatever your line of sight distance is, distance to observer, crossing through to B1, where it crosses this axis, that's how much noise they're going to be. So you can see the predicted noise level, I've written it as 59.5 because it's very close to that 60 decibel line. So I brought it down a little bit. 59 would maybe be even lower, so I split the difference and said 59.5 decibels. Okay, so that's, if there's no attenuation of sound, an easy way to get a rough estimate of how much noise this highway is going to introduce when we're 110 meters away from it. Yes? No, the heavy truck, and you don't take the average, you combine the sounds. Remember, in the last class, we went through the calculations how to combine sounds. So if you had heavy trucks and cars, there's a similar process where you're going over to the volume, and then you'd find out what the noise level is, and then you combine them using the formulas that we did last time. All right. It means to make it lower. Attenuation. Roadway noise can be attenuated by putting in a highway sound barrier. And so if there's something that normally would be transmitting noise to the side, all you have to do is put in a tall wall, and some of the noise can still get past the wall, but in this shadow zone, you'd make the shadow zone where people are going to be. So we don't care so much if the noise goes into the sky. We would make it so that the shadow zone includes houses, schools, and so on. So when we're trying to attenuate noise, there's several ways to do it. We could put up road barriers on either side of the highway, and that gives you a pretty good reduction in sound. You can see over here on the right side, that's saying how many decibels is reduced. And you know, this has a lot of different data points on it. What percentage of your traffic is trucks versus cars? And the reason why trucks are important is because trucks are higher. And so the higher the vehicle is, the more sound gets over the barrier. Not only are trucks noisier, but since they're taller, that also makes them worse for noise. So for example, if you have no trucks and you have a high barrier, 6 meters tall barrier, then that can bring the sound levels down by 14 decibels almost. If you have a depressed roadway, meaning that you excavate and put the road down and are just using the geometry of the land itself, that's not quite as effective at reducing the sound, but it still helps. Likewise with elevating the roadway, because then if the road is elevated, it creates naturally kind of a shadow zone where the people are below the sound. And so that's sometimes why highways are elevated is, number one, it allows you to put things under them, but also the noise of a highway is much less serious if it's elevated. Mm-hmm. It definitely does. That's why there's still some sound. It reduces it. But especially the low frequencies. If there's a heavy truck that's going over a bridge, you can still hear it because the larger the vehicle, the more powerful the low frequency sounds are. All right, so here's where it really gets crazy in our in-class exercise. What we're trying to do is say, well, what if we put in a barrier? How much lower would the volume be? And in the in-class exercise description, it says, let's put in a barrier that is, it has the following description: barrier position, break-in line of sight distance. What those are talking about is where is the location of the barrier compared to the traffic. So how close is the barrier to the vehicle that's making the noise? And then also, vertically speaking, what's the position of the barrier relative to where people are listening? So we're going to use this figure to go through it. What we're going to start with is identify your line of sight, which should be 110. The line of sight and the D sub C in this example are the same. And in the handout it says that the break-in barrier is 2 meters. And so find these two locations, 110 for the line of sight and break-in barrier of 2, and then draw a line through them, crossing this turn line as it's called, and then putting a horizontal line beyond the turn line. Okay, so I'll give you a moment to do that step.
So we draw a line passing through the break-in barrier from the line of sight.
Exactly. Yep.
The beginning of the turn.
And it touches the beginning. They call that the turn line. Yeah. So the 2 points that describe the line are 110 and 2. So we draw that line, oops, and we stop once it gets to the turn line, and we go horizontal. Okay? All right, let's keep moving. The next thing you do is the vertical line. Again, we use our line of sight distance of 110, and instead of the break-in barrier, this time we use barrier position. The barrier position, again, is how far away the wall is from the traffic that's making the noise. In our handout it says use a barrier position of 10 meters, and again our line of sight distance is 110. So make a line from 110 through the 10 marking, and then stop at the turn line and go straight up. Going from 110 to 10, extend the line, and then straight up. Okay? The next thing we do is we follow the curve this way. Here's the intersection of the line. Use the curve as sort of a guideline until you get to the edge. So let me show you that. So here, what I've done is here's the intersection. Follow the line and stop at this next turn line. And I've labeled that intersection as C, where when you're following the guidelines and stop at the turn line C. Okay? Then a buzzer will go off, and no. I mean, what do you? Oh, you just you follow the line. If you're not between lines, like if you're on a line, then you just follow it. Okay. So that's point C. And now there's the line of sight again. Remember, our line of sight is 110, so we're doing another intersection. From C to our line of sight, where it intersects what's called the pivot, I've labeled that as D. So D is the point that you come up with when you have the intersection of C to this line of sight distance here. Okay. Now here's what I'm going to do with point D. I'll show you the illustration in just a moment, but I'm going to go from point D sideways until I reach one of these curves. I'm going to go for the 110-degree curve because that's what it says in the handout. It says that the angle subtended is 110. What's that? I don't know. I used a really good pen, so maybe it's in my magical pen. So what I'm going to do is I'm going to go sideways until I reach the 110-degree angle. So here I'm going from D sideways, intersecting 110, then you go up, and that tells me it's a 4.2 decibel reduction in sound. So from D, sideways until you intersect the correct curve. Then you go up from there, and that's your attenuation. So in the end, if I put in the barrier, how noisy will it be? It goes from D. D is the intersection of from C to 110 as the line of sight distance. So it's where it intersects that pivot. Okay? Then you go sideways from the intersection. All right. So you can go through it again since the recording is online, but 4.2 decibel attenuation, the answer in the end is if it's 59.5 and we reduce it by 4.2, then with attenuation it should be 55.3. Don't worry if you're off by 1 or maybe even 2 decibels. There's a little bit of uncertainty because, you know, even the width of your pencil can introduce error. What's that? I don't know. Please put your in-class exercise, just the one with your name. You can keep the other one, the one that you've got all the curves on, keep that for the homework. Leave it, use it on the last problem. I'll see you in class on Thursday.